Back we are in the PLC Professor's Workshop and Lab, where we sort out all of our lab projects. This next lab project, M18 in Part 2 or Semester 2 of CCW with the Micro800 controllers, we are putting more emphasis on the simulator because we have a feeling there's going to be more people doing the projects with a simulator than with actual hardware, given that the simulator works really well and has a lot of nice features. This lab project, M18, we are continuing with the cylinder that we did in M17, but we're getting into diagnostics. One of the advantages of add-on instructions or user-defined function blocks is that the type of code that you would have written 10 years ago, 15 years ago, to do diagnostics on various motion, the customer didn't want to pay for it. In other words, if you had to quote a job and you couldn't just throw in diagnostics on cylinder motion free. In other words, you couldn't just make that part of what you do because your boss doesn't want to pay you to do something he's not getting money from the customer for. However, with add-on instructions or user-defined function blocks, you can create an instruction that does all that diagnostics. So we're going to continue looking at the cylinder in the light of putting some diagnostics on it, meaning that when you commission the process, you kind of look at how long it takes the cylinder to extend and retract under nominal conditions, and then you set up some diagnostics. That way, if that motion deteriorates, dirty slides, sometimes the operators like to play with air pressure or flow controls. I don't know, speed it up, slow it down, get a longer break, who knows why, that it'll come up and it'll warn you that the installed defined extend and retract times have deteriorated, and it can do it in two levels. It can be a warning that it's deteriorated, and then finally a fault that it's slowed way down. So let's get at it. This lab project can be found in either one of these two manuals. It's not going to be found in Part 2 of the first edition, but it is found in the second edition and the third edition. Keep in mind, if you have the second edition, that's good, but you can no longer buy the second edition of the manuals, just the third edition. So if you're watching this video without having the manuals, you're looking for the second manual there, Part 2, third edition. Real simple logic here, and of course we're moving towards a destination of having virtual cylinders in the sense that we have extended and retracted proc switches that behave like they would on a real cylinder, where there's a time delay from the time you energize a solenoid to when it actually hits the other end of stroke. If you look over here to the side in our global variables, you see that input 7 is on. Now that's IN07, not actual really input 7. If we scroll down here some to the actual inputs right there, you see 6 and 7, neither one of them are on. Logical value or physical value. But if we go back up here, you can see that the logical value for the buffered variables do respond to this logic. So let's turn on input 0. And you see that turns on output 1, and when output 1 comes on, we start our 2-second delay before we turn on input 6. Turn 0 off, and input 6 goes off right away, and then 1800 milliseconds later, 1.8 seconds, input 7 turns on. Real simple. Before we get too much further, and depending on when you're watching this lecture, this may or may not still be an issue. But at the date of this recording, the software connected components workbench with the simulator, because only the simulator can fault. CCW cannot fault, but the simulator can fault with the watchdog timer timeout. But it's really not an issue of the watchdog timer, it's an issue of how many cores or CPUs you have executing code and the computer being too fast, so fast that it misses certain hooks and then faults the processor. And I could force it to fault, but I'm not going to. Instead, I'm just going to show you how to check it. So if you do a Control-Alt-Delete, it's going to come up with this display which shows the processes. Now I have the simulator already functioning. Now I've gone through all this before in other lectures, but I wanted to throw it in here to make sure that you didn't miss it in the other lecture, which was way back in part 1, semester 1. So I'll go to the simulator first, and I'll right click on it and go to details. Okay, and you see it shows up down here highlighted. I'm going to right click and go to set affinity. Okay, you see that I have 3 CPUs checked. Typically when you open it up, it's going to look like this. All of them checked. So I uncheck all of them and then just check a couple of them. Here we're showing our logic with some edits completed according to the manual, downloaded and running. And the first thing I'm going to do is I'm going to turn on, see my mouse here, cursor. I'm going to turn on input 0 over here. Now remember, this is a single solenoid. We had a double solenoid before, but we had a single button. You pushed the button and it extended, you lifted your finger off the button and it retracted. But it extended and retracted because there were 2 solenoids that shifted the spool, and it was probably a return to center. So in other words, if you didn't have your finger on the button, then the spool was sitting in the center of the valve body. So it wasn't pushing really in either direction. We pushed the button with the double solenoid, not this one. It energized the extend solenoid and it shifted the spool in the direction to extend, to apply air pressure to the back side of the piston and extend the rod on the cylinder. And then when you released it, it de-energized the extend solenoid and energized the retract solenoid and took it back to the other extreme position for the spool. Now whether or not it was spring return to center, that would depend on some other logic that we didn't have. So the previous one was a double solenoid, and we've rewritten the code to make it a single solenoid. So you turn on input 0, output 1 is going to turn on, and when it turns on, it's going to start this timer. When it turns on, this will go false, and this timer will reset. So you can see it's timed out right now, and our simulated proc switch is showing that it's made. Now notice that instead of IN 06 and IN 07 that we had before, I have something that looks like an input, but it's really not. And this is kind of a transitional thing in my logic between having virtual and having real. Remember, I'm doing this with the simulator, but you can do this with real I/O. You can do this with hardware. And this project was originally written with a Micro810 with lights and switches 2.5, 3 years ago. And the simulator came out about a year ago. We have switched over to trying to emphasize a simulator for all of you who aren't buying hardware and want to use the simulator, because the simulator is free, the software is free. The only thing that's not free is the manuals and the lectures. But the software in the simulator comes with the software is free. So we're emphasizing that more than using the hardware, but we still need to keep the hardware in mind. Another situation is the buffered I/O. We really don't need buffered I/O with any of the applications that we're going to do, but it's a good practice to be in with most PLCs and most applications. Okay, back to this. So now we've got a single solenoid. When I turn on input 0, that's going to turn on output 1, which is going to switch these two instructions. This one's going to go true, this one false. When this goes false, this resets. When that goes true, it starts timing. And when it's timed out, so you see it instantly pulls off the retracted switch, and then 2 seconds later turns on the extended prox switch. These are simulated, virtual. When I take my finger off of the button, then it retracts. So it pulled off of the extend prox switch immediately and then went to the retracted prox switch, is where it's at right now. So we're going to, there's another way to do this, and that's with configuring the I/O wiring, where we can simulate the time delay between when you energize the solenoid and when the cylinder actually extends the rod out and you hit the extend position. There's another way to do that. We're not there yet, so we're going to continue with what we've got, and we will eventually get there. This is the next step in this lab project, and that is that we added some more code. I'm going to pull down to the bottom here. Down at the bottom here we have what we would call our virtual cylinder, and I'm going to move this up so we can see the full extent of the logic here. If we turn on the solenoid, then we have an elapsed time at the end of which we say it's extended. When we turn it off, true if off, this resets and this timer starts accumulating, and after the end of 1.8 seconds, then we say it's retracted. So this logic down here, we don't need to have in view because we know that works. We did that in our last lab project. So I'll pull this back down and I'll go bring it all the way up to the top, more or less to the top. And here is our rung that we actually operate the cylinder with. If we turn on input 0, which I'll do over here, then the solenoid comes on and down out of sight now. We have the logic that has a 2-second delay, and then this bit right here comes on in memory. Now remember this IN_10, this is kind of a virtual input representing the extended prox switch. Because this is how we're simulating the cylinder. And if I turn off output 0, then the extended prox goes off right away, and then after a short period of time, the retracted prox goes back on. Now, I'm going to reset the faults here with input 5, right here. Turn on input 5, that resets the faults. Turn that back off. Now, if I extend it, the prox comes on, no fault. If I turn it off, oh, I see I have the wrong time in there. I have 1.8 seconds, which is identical down at the bottom here. So that's why it's faulting. This is supposed to be, say, 4,500 milliseconds. So I'm going to pause this, fix it, and come back. Okay, I have the correct PT in here now, 4,500 milliseconds. It was set at 1,800, so naturally it faulted because it took 1,800 milliseconds in this, the logic down at the bottom to do the retract. So let's extend it again. And we see that this starts accumulating, but when it gets to 2 seconds, it stops because input 10, or this virtual input extended prox switch, went on. If I turn the push button off, release the push button, then this goes for about 1,800 milliseconds and then stops because the retracted prox switch made it, I should say the piston made it to the end of stroke at the retracted position. Now let's do the same thing, but first let's turn on input 4 over here, and that is going to enable the inhibit cylinder motion bit. Now you see it's not on right now. We did that on purpose because we don't want that coming on immediately, because then it would fault immediately. So it can only come on if both proc switches do not see the piston. So that means the piston's somewhere in between. Let's just say in motion. So with that on, I'm going to turn on input 0, and you're going to see this is going to go right on by 2 seconds until it hits 5 seconds, and I get a cylinder extend fault. Now I'll turn on input 5 to turn that off, to reset it. Okay, so you see we've reset. Well, we still have the extended fault because this is still true. So I would have to remove input 4 that lets it complete the motion. Because remember, that was inhibiting turning on the bit down below IN_10. So let's go back and turn that on again. And you can see that, well, we'll reset the faults. And then turn on input 4. So you can see it's on down here, sticky cylinder. Now, we're extended right now, see? IN_10 is on. Cylinder 1 extended proc switch. We'll turn this off, and you'll see that this timer will now accumulate up to 4,500 milliseconds, and then you get a retracted fault. So we'll turn off the sticky cylinder, hit the reset, and we're back at the at-rest state. Very simple logic. Next, we had you add some logic to demonstrate the move instruction. And we're also using a comparison instruction. In this case, I'm using the less than instruction. You see the symbol less than. I could have used the greater than and then just put this variable for input 1 and this variable for input 2. Because remember, this is comparison. You're comparing two. So if the previous is less than the current, then you save it. In other words, we're moving this variable, a value of this variable, into this variable. So if the relationship reverses, then you will no longer move this value into this variable. So what this does is it captures the highest value that has shown up in this variable right here, cylinder 1 extend ET. That's one of the timers that we used up above. Track, remember, we're looking to see if the cylinder takes more than 5 seconds to extend. If it does, we're declaring a fault. We've discussed that. Here we're doing the same thing on retract. So we're using these two ETs, the ET from both of these two timer instructions and these two comparison instructions. But you understand that if I wanted to use the greater than, I could say if the current is greater than the previous, then do the same thing. So you could use the less than here as I did, or you can use the greater than, but you just have to swap these two variables into their respective positions. That's all this logic does. And of course, because we have fixed times down here in this logic down below at 2 seconds and 1.8 seconds, that's always going to come up to those values. So if we turn on input 0, you see it goes up to 2 seconds. If we turn it off, you can see that it's here, but because it never exceeds that value, it doesn't replace this value. So this is a way to capture the current elapsed time for the stroke. Now we know what it is because we're doing it down here. We're simulating it so it's fixed. But if you were to change these values to change the simulated stroke time, these would change to match. However, if you lowered this, shortened it, the length of time, these would never change. You would have to make these higher in order for this to go above 2 seconds and that above 1.8. Now, once you've captured something, if you want to get rid of it, we had you, and for those of you that use RS Logics, you would normally use a clear instruction. Instead, I'm using a move 0 value into these variables. Now, something very important to remember, because we are using time data types here. So this particular one right here has to be time, because that's the ET value from that timer data type up above. And it is in a time format, T, pound, and then something in milliseconds or seconds. So this has to be. Well, for the comparison instruction, you can't have a time data type and a integer or double integer. So you can't take the milliseconds and treat it as a double integer here and compare the two. It's not going to let you do that. So rather than converting the ET into a type of integer and have these both be integers, I'm just using the time data type here, and then I declare this variable as a time data type. This is also a time data type, and you might as well do it that way. So the move can't move a time data type into a non-time data type. So you got to be careful what you're doing here. If you're an RSLogix user, you're going to try to do it the way you did in RSLogix. You can't do that in CCW for the Micro800s. So up here, I'm using a move instruction to move a time data type of 0 milliseconds into this variable and into this one. This is for the extend, and this is for the retract.